Welcome to this explainer. You know, we spend so much time obsessing over AI software, right? The massive language models, the generative apps, all that digital magic. But today, we're actually ripping open the chassis to look at the invisible, physical hardware war that is completely shifting the foundation of AI as we head into 2026. Seriously, forget the cloud for just a second. The real revolution? It's happening in the silicon right in front of you, on the edge, and in ways totally inspired by biology itself. We're looking at a fundamental decentralization of the entire hardware stack.
Here is our battle map for this explainer. We'll start with the AI physics wall, move to the decentralized silicon frontier, look at NPUs as our client-side heroes, explore the neuromorphic computing revolution, touch on event cameras, and finally, map out the physical future of AI.
Okay, let's dive into this by just looking at the sheer mind-bending scale of the hardware economy right now. Generative AI chips alone, they're projected to hit roughly $500 billion in revenue this year. $500 billion. That is nearly half of all global semiconductor sales. But here's the catch. That staggering number is actually hiding a massive structural crisis in how we do computing.
Section 1. The AI physics wall. Hitting the grid and memory limits.
For a decade, the whole playbook was super simple, right? Send all your raw data to some distant server farm, crunch it on massive GPUs, and just wait for an answer. But in 2026, this cloud-tethered model has hit a literal wall. We're talking fundamental physical, financial, and electrical grid boundaries. There simply isn't enough power, and there definitely isn't enough memory. Just take a look at this quote. It perfectly cements the stakes of the 2026 memory shortage. The hyperscalers, Microsoft, Google, Meta, they're placing enormous sweeping orders for AI server memory. Because a single AI server eats up to 20 times more memory than a standard one, manufacturers are absolutely prioritizing those lucrative contracts. The result? They are completely starving enterprise infrastructure. DRAM contract prices have absolutely spiked, and we're seeing a permanent reallocation of global silicon capacity.
Section 2. The decentralized silicon frontier. Moving AI to the edge.
Because the cloud is basically choking on its own demand right now, we're seeing this massive pivot. The migration to this nearly $30 billion decentralized market is happening because, frankly, cloud AI is noisy, it's slow, and it's totally tethered to the power grid. Think about it. Sending your raw data back and forth across the internet inherently comes with major privacy risks and high latency. But edge AI, it's stealthy. By running models locally on your own device, you're getting microsecond latency, absolute local privacy, and it literally just sips milliwatts of battery power. Plus, hey, it keeps working even if your Wi-Fi randomly drops.
But to make this edge AI actually work, the hardware itself had to fundamentally change. Let's demystify this alphabet soup of processors. Because no, you can't just throw a generic CPU at an AI workload and hope for the best anymore. AI has totally fractured computing into layers, and each layer now demands highly specialized silicon. CPUs? Those are your generalists, just orchestrating the system. GPUs are the heavy lifters for massive model training. TPUs are hyper-specialized for Google's cloud ecosystem. But the real breakout star of 2026? The NPU, or Neural Processing Unit. It's built specifically for incredibly low-power matrix multiplication.
Section 3. NPUs, the client-side heroes, AI in your PC and phone. These NPUs are the stealthy, client-side heroes making AI run locally in our laptops, our smartphones, and our wearables, all without burning hundreds of watts or melting your battery. The real catalyst for this whole NPU explosion was actually a very specific performance threshold, the 40 TOPS baseline for Microsoft Copilot+ AI PCs. TOPS simply stands for trillions of operations per second. And setting this 40 TOPS standard literally forced every major laptop vendor on the planet to build neural engines directly into their processors. It's exactly why we're seeing such rapid, crazy innovation this year, with chips like Intel's Panther Lake, built on their new 18A process, and Qualcomm's Snapdragon X2 Elite. These chips are pulling enterprise workloads right off those wildly expensive cloud GPUs and dropping them straight onto the device sitting on your desk.
Section 4. The Neuromorphic Computing Revolution. Brain-inspired silicon.
All right, let's leap beyond traditional architectures and dive into something even more radical: biological biomimicry. Now, what's really interesting about this slide is the physical bottleneck in the traditional von Neumann model. See, since the 1950s, the processor and the memory have been kept physically separated. Shuttling data back and forth between them creates this massive, unavoidable energy drain. But neuromorphic chips? They just throw that concept out the window. They literally mimic the human brain by co-locating the memory and the processing into a single, asynchronous, event-driven mesh. There's no global ticking clock. The chip only actually computes when something happens. To actually run on these brain-inspired chips, you need a totally different kind of software called spiking neural networks, or SNNs. Think of a housefly dodging a SWAT. Its tiny brain isn't processing a continuous 30 frames per second video stream of empty air, right? It only fires, or spikes, when its vision actually detects a physical change. SNNs work exactly like that. They communicate via discrete binary spikes. If nothing in the environment changes, the whole network just stays dormant, which achieves massive energy savings through extreme sparsity. I mean, imagine if your laptop only used battery power the exact millisecond you pressed a key.
And this perfectly illustrates exactly why this matters so much. Notice the staggering drop in power consumption here. For something like object detection, a traditional GPU, say a Jetson Nano, might draw 15 watts of power. But Intel's Neuromorphic Low-High 2 chip? It achieves the exact same task using roughly 0.1 watts. That is a 200 to 400 times efficiency gain. These chips, they don't drain power, they sip it.
Section 5. Event cameras and robotics. Vision at the speed of light.
So where is all this brain-inspired computing actually being deployed? Well, it's supercharging the next big piece of the hardware rebellion: autonomous robotics and machine vision. To feed these spiking neural networks, you need a completely new type of eye, the event camera. Traditional cameras, they capture full pictures, which creates motion blur and just a massive amount of data waste if the scene is mostly static. But event cameras don't capture full frames at all. Each independent pixel only fires an asynchronous signal when its specific brightness changes. That's it. This completely eliminates data waste and delivers a temporal resolution of just one single microsecond.
To really prove the superiority of this event-driven perception, just look at this incredible real-world anecdote from the University of Zurich. They built an autonomous racing drone that uses an event camera and a spiking neural network to dodge obstacles at speeds exceeding a blistering 200 kilometers per hour. Now, a traditional 30 frames per second camera has about a 33 millisecond latency, and at 200 kilometers an hour, a 33 millisecond delay means a very violent crash. But this neuromorphic system processes events at 1 megahertz, which yields a total end-to-end latency of just 3 milliseconds. It is absolutely wild.
Section 6. The physical future of AI. The strategic playbook.
So we've seen how edge NPUs and these brain-inspired neuromorphic chips are fundamentally rewiring the hardware landscape. But how does this actually translate into a practical reality for your future? I want you to ask yourself this critical question. As an enterprise buyer, a developer, or just a massive tech enthusiast in 2026, how do you bypass the electrical grid constraints and the crippling memory shortages that are choking the cloud?
So the crucial point is this exact strategic playbook. First up, you must quantize and shrink your models so they execute locally on device NPUs. This saves you huge cloud costs and guarantees your privacy. Second, you need to decouple from centralized supply chains by utilizing edge architectures that don't rely on hoarded, server-grade memory. And third, for high-frequency robotics or spatial AI, you have to harness sparsity. Move away from standard cameras and adopt neuromorphic sensing to get those microsecond reactions on a milliwatt budget.
I'm going to leave you with this provocative final thought. True AI progress. It is no longer just a software problem. It is a systems problem, all the way down to the atomic level of the silicon. This physical stealth war powering our digital future isn't happening in some massive remote server farm. It's happening right on the edge, on your desk, and in architectures directly inspired by the very brains in our heads. Thank you so much for joining us for this explainer. Keep questioning the tech behind the curtain, and we will catch you next time.